Swayam Prabha. Digital India. Educated India.
Good morning. In the last lecture, we looked at a problem at how to solve a beam problem using the displacement method. And in the end, I gave you a problem which included a support settlement, and we were going to say that we were going to look at that problem in this lecture. So let me just reiterate that particular problem. What you have is this, and the support has settled. The support settlement is 0.03 meters. So what will be the deflected pattern look like? If you look at it, where this is theta c and this is theta b, the two unknown rotations, the 2 degrees of freedom, displacements corresponding to the degrees of freedom. So theta b unknown, theta c unknown. Again, going back, what do we have? By compatibility condition, theta ab is equal to 0, theta BA is equal to theta B, delta BA. Now this is interesting. What is delta BA? Delta BA in the previous case was 0, but here you see B, A, C. B has gone down relative to A. Okay? So that means delta BA is not 0. What is it? Remember, delta BA was considered to be positive if B went up relative to A. Since it's going down, it's negative, and the value is 0.03 meters. Let's look at member BC. Theta BC is equal to theta B, theta CB is equal to theta C, and delta CB is equal to, now look at it, B has gone down relative to C. So we can say that actually C has gone up relative to B, relative. Okay, so it is plus, so it's plus 0.03 meters. Note that we are given that E is equal to 200 GPa and I is equal to 2 into 10 to the power of minus 3 meter fourth. Okay. So these are what are given. So now since we know these, we can substitute them into the equations. And what are the fixed end moments, by the way? Since there is no loading, note that fixed end moment AB, fixed end moment BA, fixed end moment BC, and fixed end moment CB are all 0. Okay? So they are all 0. So now substituting into the equations, what do we get? Well, let's see what we get. We get the equation MAB is equal to 2EI by 10 theta B plus, note that it's actually minus 6EI L squared into delta, but since delta is negative, so this is going to be 6 100 into 0.03. Okay, then MBA is equal to 4EI upon MBC is equal to 4EI upon 10 theta B plus 2EI upon 10 theta C minus 6EI upon 10 squared. Note that in BC, delta B is positive, so that's why this is this way, and CA 2EI upon 10 theta B plus 4EI upon 10 theta C minus 6EI upon. Okay, so if I plug in the values of EI, see what I get. I get it equal to MAB is equal to 2EI upon 10 theta B You see, you plug in the value of EI. Note that I'm just going to go through a little bit. Let me show it to you. You might be a little bit confused. You see, what I'm doing is 6 EI upon 10 squared into 0.03. So EI is 200 GPa, which if you write it in kilonewton, see, note that everything is in kilonewton. So if I write in kilonewton, 200 GPa is equal to 200 into 10 to the power of 9 Newton per meter squared. So this is going to be equal to 200 into 6 kilonewton per meter squared divided by 100 multiplied, this is 100 meters squared, okay, multiplied by I. What is I? 2 into 10 to the power of minus 3. That is 6 EI upon L squared. This is, units are meter fourth, and then we have 0.03 meters. Let's see what units I'll end up getting. If you really look at it, this is going to be equal to kilonewton. This is going to be meter fourth at the bottom. Meter fourth cancels here, so it's going to be kilonewton meter. So these units, if you look at this, this goes into this goes into this 3 times, okay, and this 3, if I bring it here, this will become 1, so this will become 6 into 6 36, 36 into 2, 72 into 10, 720. That's what I have over here. So this is 720 kilonewton meter. So these are the units, and then 4 EI upon 10 theta B plus 720 kilonewton meter. MBC is equal to 4 EI upon 10 theta B plus 2 EI upon 10 theta C minus 720, the same, and then MCB is equal to 2 EI upon 10 theta B plus 4 EI upon 10 theta C minus 720. Now the equilibrium equations are the same. Okay, so the equilibrium equations are MBA plus MBC is equal to 0 and MCB equal to 0. This gives us that MBA plus MB is equal to 8 EI upon 10 theta B plus 2 EI upon 10 theta C. If you have plus 720 minus 720, so that cancels out. This becomes 8 EI upon 10 theta B plus 2 EI upon L theta C is equal to 0. And the second equation, MCB equal to 0, gives us 2 EI upon 10 theta B plus 4 EI upon 10 theta C is equal to 720. Okay, solving for this gives us that theta B turns out to be equal to minus $514 upon EI radians, and theta C is equal to 2057 plus 2057 upon EI radians. What does that mean? That if I were to draw the deflected shape over here, due to this settlement, the system becomes this way. This is positive, I mean it is clockwise because this is negative, and this is anti-clockwise because it is positive. Okay, so this is the deflected shape. And now once we get theta B and theta C, we can substitute it back into the equations for MAB. In other words, once I found out theta B and theta C, I can substitute theta B and theta C into these equations, plug in the values of theta B, and my final MAB is equal to plus 617.2 kilonewton. MBA is equal to plus 514 kilonewton meter. MBC is equal to minus 514.4 kilonewton meter, and MCB is equal to 0 kilonewton per meter. And once you get these moments, then you can draw the bending moment diagram just as we had done it last time. It's not very different from what it's not at all different from what we had done, excepting that there is no loading. The interesting point to note here is that if you look at this, how much did the moments come out to be? Think about the loading. You had 120 kilonewton loading, and then we had 500 kilonewton on 10 meters. And what kind of react forces did we get? We got much less moments than we got due to a settlement of only 3 centimeters. Okay? So in other words, settlement problems can actually give rise to significantly higher stresses in structures than loads can. And that is the reason why, okay, that support beams are always very support settlement can have very differential support settlement, okay, can have extremely problematic consequences for your structures unless you design them for these kinds of loads. Okay, so much for this particular structure analysis. I think I have done enough number of problems for beams, and what I would like to now do is I would like to go on to solving a particular problem for a frame, so that it gives you an idea of how the whole concept of frames, the displacement method can be used for frames. And you will see another very interesting thing, and that is that for frames, since in a beam, we only had theta AB and theta BA. Okay? In frames, you will see that delta BA will also come in, and it will be an unknown. See, in a beam, the only problem that we did where delta BA came in was when we had support settlement, where we knew the value of delta. In frames, you will see that that will also be an unknown, and therefore you have some interesting equations of equilibrium that you have to develop when you go through. So let me take a very simple problem and go through with it for you. Okay, so this is okay. This is a frame that we have, and if you look at this particular frame, what it does is it's supported fixed supports at A and D, and it's a single story, single bay frame with an overhang. Okay, and at the end of the overhang you have a load. You have one load in member BC. So if you look at it, so therefore member AB has a load, PC has a load, CE has a load, and CD has a load. Now, in this particular case, you will see that I am going to eliminate CE because I am not quite interested. You see, if you look at CE, can I draw the bending moment diagram for CE? Sure, I can. At this point, bending moment is going to be 0, and at this point, it's going to be 50 into 5, 250 kilonewton meter. So therefore, this is not, I know the bending moment in here, so I don't really need to know I don't need to consider this. So what I'm going to do is, I'm going to consider that this load is going to get transferred to C with the appropriate equivalent forces. So if I look at this, with this problem, I can solve it as far, so I need to only solve A, B, C, D, okay, with given fact that the loading from CE comes out to be this. If we look at it, I can solve this problem. (15 meters, 20 meters), load here, and this load I can transfer here as 50 kilonewton. But just transferring the load is not good enough. What happens? Equivalent load system, I also have to transfer a moment, and the moment is equal to 250 kilonewton meter. So you see, now I am solving A, B, C, D. Okay. So this is the problem that we have to solve using the displacement method. What's the first step? First step is to find out the degrees of freedom. Now, how do we find out the degrees of freedom? Again, let me go through all the steps of the degrees of freedom. How many nodes? 1, 2, 3, 4. So 4 joints, 3 into 4 is unrestrained degrees of freedom, 12. How many restraints? Restraints are 3 here and 3 here, because restraints, you're restraining all 3 degrees of freedom at this point, and you're restraining all 3 degrees of freedom. So total 6 restraints. Constraints, I have 3, axial deformation is neglected, 3 members, 3 constraints. So how many degrees of freedom? 3. What are those 3 degrees of freedom? Well, theta at B, theta at C, and delta. So this delta can be, this delta is the same as this delta, okay, because BC cannot actually deform. Okay, so let me do that again, that I have theta B, theta C, and delta. Okay. Now I am going to introduce some concepts, and that is that what do those, in other words, see, before I write down the slope deflection equations, I have to be able to relate these with respect to the member end deformations. Okay, so for that I am going to now start a new procedure by which I am going to find out, given each degree of freedom, how does the displacement occur, so that I can always write down in terms of that displacement what the member end displacements are. Okay, and then when I take all 3 of them together, that becomes a sum total. Okay, so here I am going to be drawing what happens when you have theta B. I'm going to put, You see, since I need to evaluate it together, I'm going to draw it piece by piece. So theta BA is equal to 1. How will the displacement look? Theta BA is 1. So it's going to go like this. This is going to go like this. See, this point cannot go because delta is equal to 0 and theta C is equal to 0, so this has to be fixed. And then this remains exactly this way. So this is my 1, 1. Okay? And let me write down all the member end displacements relative to that. But first I will draw all of them and then I will write them down. Let me put theta C equal to 1. What is theta C equal to 1? You will see that if theta C is equal to 1, then this will go like this. This will go like this. And this will come here. Okay? And then finally, delta is equal to 1. So delta is equal to 1 is going to be this way. And note that when delta is equal to 1, theta B and theta C equal to 0. So this is going to go this way. The reason why I am doing this is that, if I show all of them together, it's going to look very, very complicated. Okay? So what I do is, I take each one separately and then I know that all three act together. So once I know all the shapes for this is equal to 1 and here this is 1 and this is 1. Okay? So once I have this, okay, I can write down each and every, for member AB, what are the deformations in terms of theta B, in terms of theta C, in terms of delta. Okay? And now, with this, look at how their deformations go. I am now going to write down the kinematic relationship, and that is what for member AB. What is theta B AB equal to? If you look at this, remember theta AB is always going to be 0 because at that particular point you have theta B is equal to. What is theta B equal to? Let's look. Theta B A is equal to. Let's see theta B A. Theta B A, when theta B is equal to 1, theta B A is equal to 1. So theta B A is equal to 1 into theta B. When theta C is equal to 1, theta B is equal to 0. When theta delta is equal to 1, theta B is equal to 0. So therefore, we are going to write down theta B A is equal to theta B only. Similarly, write down delta B A. When theta B equal to 1, what is delta B A? 0. When theta C is equal to 1, what is delta B A? 0. When delta is equal to 1, what is theta B A? Let's look at this. Delta B A B. So A B has to go up this way for it to be positive. It's going down, so it is actually negative 1. So it is minus delta. Okay? Similarly, let's look at member B, C. What about member BC? Theta BC is equal to, what is BC equal to? Let's look at it. BC is equal to 1 into theta B plus 0 into theta C plus 0 into delta. So that means theta BC is equal to theta B. What about theta CB? Theta CB is equal to 0 into theta B plus 1 into theta C plus 0 into delta. So it's equal to theta c. Similarly, delta CB, delta CB, C relative to B, 0 theta B plus 0 theta C plus 0 delta. Note that this has to move this way for it to be delta, so it is, so delta CB is equal to 0. Member CD. Now I am looking at member CD, so this is where I am looking at it. Okay? So if you look at it, I am looking here to here. What is member CD? Delta B, CB, CD is equal to 0, delta theta B, plus 1 theta C, plus 0 delta. So this is equal to theta. Theta DC, fixed end, 0. Delta DC is equal to, let's look at it. Delta CD is equal to 0 into theta B plus 0 into theta C plus, now let's look at this, what this means. If you really look at it, CD, D has to move this direction for it to be positive delta. However, if you really look at it, since this has gone up, we can say that relative to C, this has actually gone this way, so it is negative delta. So it's negative delta. Okay, so we have now got all the relationships between the member displacements, the member end displacements, and the degrees of freedom, theta B, theta C, and delta. Okay, so now we substitute these into the equations. But before we substitute that into equations, we have to find out the fixed end moments. So we have to find out the fixed end moments in AB, BC, and CD due to the loads. Now remember, AB has a load, right? What is the load? AB, this is AB, 10 meters, 5 meters, and at this point we have a 20 kilonewton force. Okay? So if you look at it, what is this going to give me? The fixed end moment at AB is going to be equal to what? It's going to be equal to P, and note that this is going to be this way, this is going to be this way. So this is positive, so this positive is going to be plus 20 into 5 squared into 10 upon 15 squared. Okay? So if you look at this, this is going to be equal to 22.2 kilonewton meter. BA is going to be minus 20, it's negative 20 into 10 squared into 5 upon 15 squared is going to be equal to minus 44.4 kilonewton meter. Okay, now let's look at what happens in BC. BC has 100 kilonewton force acting 8 meters, and this is 12 meters. So this is going to be this way, this way. So fixed end moment at BC is equal to plus 100 into 12 squared into 8 upon 20 squared. This is equal to plus 288 kilonewton meter. Okay, so and then fixed end moment at CB is equal to minus 100 into 12 into 8 squared upon 20 squared. This is going to be equal to minus 192 kilonewton meter. Now look at CD. CD does not have any load on it, so FE, the fixed end moment in CD and DC are going to be equal to 0. Okay, so let us look at the equilibrium equations. If you look at the equilibrium equations, what we get is that MAB is going to be equal to 2EI upon 15, 2EI upon 15 multiplied by theta B and then plus 6EI upon 15 squared into delta plus 22.2 kilonewton meter. MBA is equal to 4EI upon 15 theta B plus 6EI upon 15 squared delta minus 44.4. Okay, then we have MBC is equal to 4. Now note, it's 4 into 4. The EI itself is 4 EI. Okay, remember that? So it's 4 into 4 EI upon 20 into theta B plus 2 into 4 EI upon 20 theta C and plus 288. Note that delta is equal to 0, so it doesn't contribute. Theta CB is equal to 2 into 4 EI upon 20 theta B plus 4 into 4 EI upon 20 theta C minus 192. Okay, and then finally MCD is equal to 4, now again EI only, upon 15 theta C plus 6 EI upon 15 squared into delta. Note that it's minus again, so it's minus minus plus, and that's it. There's nothing else. There is no fixed end moment, and MDC is equal to 2 EI 15 plus 6 EI upon 15 squared delta. Okay, so these are all the moments that we have. Okay, so we've been able to write down the moment. These are the member end moments in terms of the unknown displacements that we have. Okay. So once we have done that, okay, then we have another aspect. Now, equilibrium. Now here, equilibrium is going to get really, really complicated. Let's look at what equilibrium actually entails. And again, now I'm going to separate it out so that you can understand what I am trying to say. So I'm separating out all the members from the joints and representing them separately. Okay? And now if you look at it, I'm first putting down all the moments that we have computed and all the forces that we have. So these are the moments that I have just I'm putting them all in the positive. See, this is MAB, this is MBA, this is MBC, CB, MCD, DC. Okay? So this happens to be MAB, BA, BC, CB, CD, DC. These are the values that I have already put down just now. These are all in terms of theta B, theta C and delta, the unknown displacements corresponding to the degrees of freedom. So I've put them down. Now what I need to do is, I need to actually put down all the other forces that I have on the system. So if you look at it, this one has 20 kilonewton here. Okay, then what else do I have? I have, let me just look back at the problem itself. I have 20, then I have 100. Now in addition to that, I have 50 and 250 kilonewton meter here. Anything else? No, that's it. Okay, these are all the loads. Okay, so now what I need to be able to do is write down the equilibrium equations and note that what are the equilibrium equations? One equilibrium equation obviously is moment equilibrium. So summation of all moments at B equal to 0. This, if you look at this, is going to give you that MBA plus MBC is equal to 0. Similarly, one is moment. These are the, see, note, what is this moment? This is corresponding to the rotation. This corresponding to this rotation, MC is equal to 0, and that's going to give you that MCB plus MCD is equal to 0. Okay? Is it? No, it's not. MCB plus MCD plus 250. So, plus 250 is equal to 0. Note that when you're taking equilibrium, the external loads also have to come in. So, it's plus 250 is equal to 0. These are the two equations corresponding to the two rotations. Now, I have a displacement. Corresponding to that, what do I have? Well, I have to write down an equation which says reactions have to be equal to 0. And what reactions have to be equal to 0? Well, let's see. If I take the reaction that I get here, and let's see what I get. If you look at this, this is going to be like this. Okay, so the loading will be like this. So let me just put it this. Okay, So this is going to be this way, so this is going to be this way, so this is going to be this way. And similarly, you'll get it over here. This goes this way, so this has to go this way. This will go this way, so this has to go this way. So the other equation that we get is, if you look at it, is going to be that this force plus this force. What is this force? This is the reaction at A, and this is the reaction at D. Okay? The other equation is corresponding to this delta, so it's going to be sigma Fx equal to 0 of the entire, and that's going to give me Ra plus Rd minus 20, this is the force, is equal to 0. So this is my third equation, which essentially is this. Look at the other reactions. This is Va, Vd. The other equation, Va plus Vd, okay, is equal to 100 plus 150 is not going to give me an additional equation. We will see that, why that doesn't give me. Because note that, see, you'll always see that since you have a rotational degree of freedom, you have a moment equilibrium at B. Since you have a rotational degree at C, you will have a moment equilibrium at C. Rotations go with moments, okay, and displacements go with forces. So since the displacement is in this direction, I need a sigma Fx equal to 0 to be able to generate that, and that is the reason why I have. If I had any degrees of freedom in this direction, then I have to take Va plus Vd. Okay, so that is the overall scope of things. Now once you have these I know I can substitute them in. Okay, this one I have to derive, I can find out. How do I find this out? Well, I can find out that this is going to be equal to VAB, Ra is equal to VAB, okay, and Rd is going to be equal to VDC. So I can find out these from this equation. So if you look at this, what is Va equal to? Well, let me evaluate that. Va is going to be equal to VAB is going to be equal to, I can easily evaluate it, it's going to be MAB plus MBA divided by 15. These are the moments of reaction due to this, plus 20 into 5 upon 15. Okay, so that's going to be VAB, and then VDC is just going to be equal to MDC plus MCD upon 15. Okay, and you know MAB, MBC. If you put all of these together, what you get is, see, MBA plus MBC gives you, let me write it down, MBA plus MBC gives me 4 EI upon 15 theta B plus 16 upon 20 EI theta B. Okay. 4 EI plus 16 plus 8 EI over 20 theta C plus 6 EI upon 225 into delta plus 243.6 is equal to 0. That is my MBA plus MBC. And if I look at MCB plus MCD plus 250 equal to 0, MCB is going to be equal to 8 EI upon 20 theta B plus 16 EI upon 20 theta C plus 4 EI by 15 theta C. Okay, plus 6 EI upon 225 delta, and then plus 250 minus 192 is going to be equal to 58 equal to 0. That's my second equation. And my third equation is going to give me that is going to give me this plus this minus 20 is equal to 0. Okay, now you can evaluate that. I'm not going to go into that detail. I'll leave it up to you. In fact, what I can do is, if you look at this, since these are all divided by 15, I can just multiply by 15 over here, and I'll get MAB. If you look at this, from this equation, I get MAB plus MBA plus MDC plus MCD plus 300 is equal to 0. Okay, because all I have done is I multiply that, minus 300. Minus 300 is equal to 0. And all I need to do is substitute all these terms in, and then essentially, if you look at this, let me do that. Okay, I mean, why stop it at that? I'm going to put that equal to 2 EI by 15 theta B plus 4 EI by 15 theta B. Okay, then okay, that is 4 EI by, so that's 6 EI upon 15 delta B. Okay, plus, now if you see MDC and MCD, okay, it's going to become, I'm going to just put it in 6 EI upon 15 theta C. Okay, and then if you look at it, it's going to be equal to plus let me just go back. MAB has 6 plus 6, then I have MCD has 6 plus 6, so this is going to become equal to 24 EI upon 225 delta. Okay, and then I have 22 minus 44, that's minus 22 plus minus 22 plus minus 300, so this is going to be equal to minus 322.2 equal to 0. Okay, so now I have three equations. If you look at it, I'll just put it down finally in an equation format. We look at it in an equation format. This is going to be theta B, theta C, delta, and on the other side I'm going to have the values. It's going to be minus 243.6, minus 58, plus 322.2. And in here you will have all the expressions. For example, this plus this, okay, I can take EI outside, and so EI will be 4 by 15 plus 16 by 20, 8, 6 by 20, okay. So 0.8 plus this thing gives me 380, and this is going to be 16 by 15, okay. So 60. So this is by 60. This is 16 plus 48. Okay. So 64 by 60. This is going to be 8 by 20. This is going to be 6 by 225. This is going to be 8 by 20. This is going to be again the same, 16 plus 48 upon 60 is going to be 6 upon 225, and this is going to be equal to 6 by 15. Six by 15 is going to be 6 by 15, and this is going to be 24 upon 225. So this equation, if you solve for it, you can get theta B, theta C, and delta. And I'm not going to go through these details. I'll leave it up to you to solve it. And once you get theta B, theta C, and delta, you can find out these values. And once you find out these values, you can always draw the bending moment diagram for the given frame. Okay? So the only thing, that difference that we had in a frame was that the displacement, in a beam, you only have rotations as degrees of freedom. In a frame, in addition to rotational degrees of freedom, you also have displacement degrees of freedom, and therefore corresponding to displacement, when you take equilibrium corresponding to rotations, you take a moment equilibrium equation. Corresponding to a displacement, you take a force equilibrium equation. Okay, and that is how you go about solving it. Okay, I'm going to spend some more time over the next couple of lectures looking at a few more problems and seeing how we can solve those. Thank you. I hope I have been able to explain a little bit over the last two lectures on how to use the displacement method to solve beam and frame problems. Thank you.